All right, the other way of dealing with this is by using the steady state approximation. So the fast reversible, what we do with the first step is just assume that the rate of the forward reaction is equal to the rate of the reverse reaction. That's fast reversible. For steady state, we make a slightly different assumption. And the slightly different one is that the rate of consumption is equal to the rate of production. All right, let's start off with the rate of production. When we're producing the intermediate N2O2, what steps produce it? And so if we break down the steps here, we have, in step 1, we have the forward reaction and we have the reverse reaction, K1 and K minus 1. And so looking at the forward reaction, that produces N2O2. Looking at the reverse reaction, that consumes N2O2. Then we have this third step here, and this is the step 2 forward reaction that consumes N2O2. And so it looks like the only place it's produced, the N2O2 is produced, is in the first step. And so the rate of production is equal to K1 times NO squared. This is a simple equation. The rate of consumption, we're consuming it in two ways. We got K minus 1, and going and taking that the first step backwards, we got K minus 1 N2O2. And the second way we're consuming it is via K2. K2 N2O2 times O2. And so we consume it here and we produce it here. So the rate of consumption is equal to the rate of production. So if we take the production rate and then subtract the consumption rate here, so let's take the production rate and subtract the consumption rate. This is what we get. And so again, the order of the reaction is given by the slow step, or not the order, the rate law for the reaction is given by the slow step. And this is the overall rate of the reaction. The problem is we have this intermediate here. We've got to get rid of the intermediate. And so this is the way we're going to do it. This is the change in the N2O2 over time. Here we have production, that is K1 NO, minus consumption, So if we take the rate of production minus the consumption, then the net change should be 0. And so this is why it's called the steady state approximation. So what we're going to do is we're just going to solve this equation for N2O2. So if I solve that equation for N2O2, I just rearrange this algebraically. Here. So we'll just factor out the N2O2 out of this. So we get N2O2 times K minus 1 plus K2 times the O2 concentration is equal to K1 times the NO concentration squared. And then we're going to divide both sides by this term here. If we divide both sides by that term, then we're going to get this. We're going to get that the N2O2 concentration is equal to K1 NO squared divided by K minus 1 plus K2 O2. All right, once we have this, then what we'll do is we'll just substitute that back into the rate law. And so let me do that here. Formatting came out a little bit weird. And so this is the equation I just wrote. So we solved that equation for the N2O2, and then we're going to substitute that back into the rate law. And we get this equation here. When we look at this equation, does this equation match the experimental rate law? So this is kind of our theoretical rate law that we got by this mechanism in the steady state approximation. And when you look at it, it doesn't match because, you know, we have this denominator with O2 in here. And our experimental rate law just had NO squared O2. And so it looks like this doesn't match. It looks like it doesn't match, but it actually does match because of this. The way we visualize the fast reversible versus the steady state approximation. Let's take a look at the difference here. The way I think about the fast reversible is like this. I imagine that step one is like a balloon here. And it's fixed. There's a forward and a reverse here. And so this is my step one. I have some air in a balloon. And then step two is there's a tiny little pinhole leak here in the balloon. And so step two is a tiny leak. And so most of the N2O2 is in the balloon here, and a little tiny bit of the N2O2 leaks out of the balloon. In other words, step two is very slow. Step one is very fast at that equilibrium. And therefore, when we do fast reversible, the rate of the forward is equal to the rate of the reverse. So the forward was K1 NO squared. The reverse is K minus 1 N2O2. And so because of conservation of mass, all the nitrogen and oxygens are tied up here because if the rate of the forward reaction equals the rate of the reverse reaction, we can't be losing any nitrogen atoms, we can't be losing any oxygen atoms out of this. But in reality, we are because this is step one. In step two, a little bit of those N2O2s are leaking out. And so we say that this is kind of a negligible leak. We lose a little bit of the N2O2 that gets leaked out and forms ultimately our product. And so the fast reversible kind of assumes that step two is negligible, but step two has to be, you know, somewhat significant, otherwise we're going to end no product. For the steady state, we don't make that assumption. For the steady state, we can have a tiny pinhole leak or we can have a more significant leak. And so steady state might mimic the fast reversible if this is a tiny leak. If we have a tiny leak, then this is what we say. If we have a tiny leak, then step two is very slow. Slow leak of N2O2. If step two is very slow, that means its rate constant must be very small. And so if K2 is very small, then very small times this gives us very small. And so what we can use is we can use the simplifying assumption. That is K minus 1 plus this term, which is very small, is just equal to K minus 1. So if this term drops out due to the simplifying assumption, then it looks exactly like the rate law we got from fast reversible. However, if the leak is big, then we can't assume that K2 is small. If the leak is big or more significant, then K2 is larger. And so if we have a big leak here, let's just go the opposite extreme. If we have a big leak here, then this term is big, and we'll use the simplifying assumption here. This term will drop out. So if we have a big leak here, then the O2 drops out. And it just depends on how fast we can produce N2O2. The rate is going to. because it's leaking out so fast that if we can't produce much N2O2, then we can't sustain the balloon. And so this would be the steady state. So the fast reversible is just a simplification of the steady state in which this term drops out. Okay, but the steady state would give us a more complete picture of the kinetics, what's going on. So here are the two scenarios that we have. One, the pinhole leak of the step 2 is very small. Step 2 is very small. We end up with this equation down here, same as fast reversal. That is K2 is very small compared to K minus 1. The other assumption is K2 is significant. A significant leak, step 2 is significant. We end up with this equation here. It just depends on how fast you can make it into O2. Kinetics is used to model more complex reactions. Here's a more complex reaction with smog, photochemical smog. This shows, the concentrations of components of smog over time. The kinetics will allow you to map this out. We aren't going to do it. More complicated. Here's some of the reactions of smog. Some more reactions of smog. But one of the ways we can get rid of smog is by using catalytic converters. And what catalysts do is they speed up reactions. So for example, carbon monoxide and NO react very slowly, but in the presence of a catalyst, we can get carbon monoxide and NO to react very quickly. Carbon monoxide is produced by incomplete combustion of fuel. NO is a precursor to photochemical smog. NO is produced in car engines by the reaction of nitrogen and oxygen at high pressure and high temperature. And so rather than having these components which will lead to smog, what we can do is get a catalyst, run those through, and that promotes the formation of CO2 and N2 rapidly. CO2 and N2 don't lead to smog. N2 doesn't lead to anything, but CO2 does lead to greenhouse gases. And so what are catalysts? Catalysts are things that help the reaction speed up. And the way they work is they lower the activation barrier. So catalysts can be something as simple as H+. This is called acid-catalyzed formic acid decomposition. So formic acid decomposes into carbon monoxide and water. Okay, without acid, this is an uncatalyzed reaction. Without the acid catalyst, the activation barrier is quite huge here. So we can see that here, because what we'll try to do is we'll look at the mechanism of the uncatalyzed reaction. And so if we have formic acid, the Lewis structure for formic acid, something like this. Now, it's going to have some energy here. But this molecule is not static. This molecule has energy. It has vibrational energy, translational energy, and rotational energy. And the energy isn't always the same. So if we look at vibrations, not all molecules are vibrating at the same energy. Some are vibrating at very high energy. So let's say we had a high energy vibration that brought this lone pair is an sp3 orbital, and pushed it into the s orbital on hydrogen. This is an sp2 sigma bond, and kicked these electrons off onto carbon. And so we just have this big vibration that pushed these lone pair into here and break this bond here. And we're going to end up with something like this. This is a potential transition state here. Something like that. Does that look very stable to you? No, this is a high energy, so this bumps This high energy. We have some formal charges here. A negative formal charge on the carbon. Let's put that in black. And a positive formal charge on this oxygen. That's not very stable. And so what we can do is we can further rearrange this here. That is, this oxygen is highly electronegative because it's got a positive charge now. So that's going to pull these electrons off here. If it pulls these electrons off here, carbon has less than an octet. And so we drop this lone pair into the bond here to maintain the octet there. And so what we're going to get in the end is carbon monoxide and water. Looks like they're about the same energy here. But you look at this, you know, how probable is this and how much energy does that take? Well, this is going to take a lot of energy here to do that. Because what we have to have is we have to have this oxygen within the molecule pluck off that hydrogen from carbon. Now, if we add an acid catalyst, what the catalyst does is it provides an alternate mechanism. And if the alternate mechanism has lower activation energy, actually, just leave it here. Do it over here. So rather than having this oxygen pluck a hydrogen off that carbon, what we're going to have is this. We're going to add some acid to this. Let me move this over a little bit. Here. So how hard now is it for this oxygen to pluck the hydrogen here? Well, it's not really plucking, it's plucking it off of water. It'd be hydronium. So it takes it off the hydronium, but it shouldn't be hard. Oxygen versus oxygen. And so is that going to result in a very big activation energy? No, not really. What we're going to get is something like this. Okay, this is not so stable because now the oxygen has a positive formal charge. Here. All right, so then what can happen, is this. This oxygen really wants these electrons, so it pulls the electrons off here. And we end up with something that looks like this. Water, which is good. But we have this species. Now that carbon doesn't have a full octet. And the carbon also has a positive charge here. And so plucking those electrons off that carbon is going to cost some energy. There's a hump here. But this is not so stable here, and so this has got to rearrange as well. So what are we doing here? What we're going to do here is we're going to have this carbon pluck the electrons off that. But it still doesn't fix the problem with the octet. And so to fix the problem with the octet, we need a lone pair to drop into the bond. So if that carbon plucks the electrons off the hydrogen here, we're going to be left with H+. And then a carbon monoxide, and then a water. So when you look at the individual steps here, you know, the individual steps here don't have as much energy required as this individual step here. And so having the acid catalyst will lower the activation energies, which will speed up the reaction significantly. And so the interesting thing about catalyst is here we consume the catalyst and then we spit out the catalyst again. And so there's no net consumption, but it is consumed and then it's produced later on. All right, this is an example of homogeneous catalysts. Homogeneous catalysts are in the same phase as, so this is aqueous formic acid. We have aqueous acid. There's also heterogeneous catalysts. Heterogeneous catalysts are in different phases. So the reactants in this case are gas phase, NO and carbon monoxide. NO and carbon monoxide components are smog. The catalysts here are typically transition metals. Transition metals are often used because transition metals have empty d orbitals. And so the first process in catalysis is adsorption. So the reactants are adsorbed on the surface. So you can see that here, this barrier, and then drops down. The next phase is the surface reactions. The electron densities, electron clouds, and electron densities can be pushed into these empty orbitals, which facilitates reaction here. And so we have surface reaction, there's a barrier for that. Once we form the products, then the electron density distribution changes, and these desorb off the surface. So we have desorption. Adsorption, surface reaction, desorption of the processes here. This is not a very detailed mechanism. It's not really showing what's happening with bonds or the electrons. And a lot of this catalysis isn't that well understood. But one thing that's understood is it significantly speeds up the reaction, because without a catalyst, NO and CO react very slowly and have a very high activation barrier. With a catalyst, the activation is very significantly reduced, increasing the population significantly for reaction. And so here's an example. This is not gas phase, this is an aqueous phase reaction. But this is just aqueous hydrogen peroxide. Hydrogen peroxide normally decomposes slowly, so the bubbles form slowly. But if you add a catalyst like platinum wire in here, then we get rapid reaction occur. And so there must be some absorption on the surface of platinum, surface reaction, and then desorption of the products. We have biological catalysts as well. Here, this blue structure is an enzyme or biological catalyst. The green structure is the reactant molecule or substrate. It turns out, due to the structure and the interactions, not every molecule fits there. For example, transition metals aren't very selective, but biological catalysts are highly selective. So selective they call it locking key. Because when you look at the catalyst structure, there's certain structures and certain electron cloud distributions. That is, certain atoms are in there, and so there's going to be an attraction here with the reactant molecule. And so again, the enzyme is the catalyst, the substrate is the reactant. So the reactant gets absorbed onto the catalyst here, and then there's some kind of surface reaction here. What happens here is that there's strong intermolecular or interatomic or whatever attractions, electrical attractions here, and that puts like a stress on the bond, a tensile stress, so there's pulling apart on the bond. As the bond's being pulled apart, it's easier to break. And so we form the enzyme substrate complex, which is just like a surface absorbed molecule or activated reactant. And then once the bond breaks, the electron cloud gets redistributed, and there's no longer these attractions, and the product is desorbed off the surface. When we look at the kinetics of this is two-step. It's a two-step mechanism. The first step is the enzyme and the substrate come together to form the enzyme substrate complex. This step we can say is fast and reversible, here. The slow step is going to be breaking this bond. And so that's the second step here. The enzyme substrate complex breaks the bond to reform the enzyme, but also form the products in this case here. That's step 2. There are 2 ways of handling this. we're going to say the second step is slow, the bond breaking step here is slow. And therefore, for the first step, the two ways we can handle the first step are fast reversible or steady state. Because the problem is the second step is going to depend on the intermediate. The intermediate here is ES, the enzyme substrate complex. We got to get rid of that. And to get rid of that, we can use fast reversible or steady state. We're going to use steady state. And so here's the steady state equation. Ignore that. So this is the overall reaction just written in one line. Step 1, step 2. The overall rate of reaction, this is the formation of products with time delta P over delta T, is equal to K2, the slow step, times ES to the first. It's first order in ES. We can't have the intermediate there. And so what we do is we're going to do the steady state approximation. That is, this is production of ES. So ES is produced by K1. But ES is consumed by K minus 1 here, and K minus 2. And so production minus consumption should equal 0. So steady state approximation. Now, once we have this equation, then we add this to both sides, and then we factor out an ES, and then we solve for that and substitute it here. But for enzymes, we do something different. For enzymes, we're going to do a little different thing, and that little different thing is this. The total enzyme in this mixture is the free enzyme combined with the complex enzyme. And so the one thing we're going to do differently for enzymes is we're going to come up with the total enzyme. The total enzyme is how much enzyme you have at the beginning times 0. And the total enzyme is going to equal the free enzyme concentration plus the enzyme substrate. And so this is similar. You know, the total concentration enzyme is the sum of all the enzyme containing species. Well, there are only 2 enzyme containing species here, and that's it. So we go back and we solve this equation here for ES. But before we complete this, we do one more thing. And that is, we figure out the free enzyme concentration. And so we just solved this equation for free enzyme. The free enzyme is equal to the total enzyme minus this complex enzyme. And so here, the free enzyme concentration at any time is equal to the total enzyme you added in the solution minus the enzyme that's complex or in that enzyme substrate complex. Okay, then what we'll do is we're going to substitute this in for E here. And so E here is going to be the total enzyme you had at the beginning minus the enzyme that was complex. And now we're going to solve this for ES. Which gives us this. The only difference between this and the previous one is now we're looking at the total enzyme initial. You know, how much enzyme there was at the beginning. Different. So we'll plug that into our rate law and then simplify. And so plugging in the ES, so the ES is going to be in terms of the total enzyme here, and then simplifying. What we'll do is we'll take these K's here and call that big K. And M stands for the person, one of the people who developed this equation. This equation is called the Michaelis-Menten equation, so that's why there's an M there. And this describes enzyme catalyzed reactions here. And that is the rate of product formation is going to depend on the total amount of enzyme we have at the beginning and how much reactant we have at the beginning. And it shows this characteristic behavior. At low substrate, at low reactant concentrations, if we double the reactant, the rate doubles. And so each time we double the reactant, the rate doubles. Low. However, when we get to higher and higher reactant concentrations, we'll double the concentration of reactant, but nothing happens to the rate. And so the funny thing about this reaction is it starts off as first order in terms of reactant or substrate, and then it goes to zero order. And so the analogy for this is this. Let's say there are only 10, let's say 10 checkout stands at the supermarket, right? And so if there are 2 people checking out, then you'll get 2 people through. If you double it to 4 people, then you've just doubled the rate of people checking out. But you can't keep doubling it. So if we double it again, we get 8 people. Well, 8 people will go through. If we double it again, we'll get 16 people. Will the rate of people checking out double? No. All of a sudden, we've run out of checkout stands. So this is the phone booth analogy. The phone booth analogy is, if you have 10 phone booths, you can only make 10 calls at a time. And each call is going to take a certain amount of time, so there's a cycle time. Just like each enzyme reaction is going to take a certain amount of time, and the others have to wait. And so basically, this is what happens. It will double, each time we double, it'll double until we run out of enzyme. When we run out of enzyme, it doesn't matter how much substrate you add in there, you can't process it any faster than you can. So we could have 100 people trying to check out, but if there are only 10 checkout stands, it's not going to go any faster than if there are 50 people trying to check out with 10 checkout stands. And so the way we visualize this using this equation is like this. At low substrate concentrations, then the simplifying assumption says Km plus S. If S is very small, S drops out. And so at low substrate concentrations, if we double the substrate, the rate of the reaction doubles. If we quadruple the substrate, the rate of the reaction quadruples. However, at high substrate concentrations, then the opposite simplifying assumption works, where Km drops out. And so at high substrate concentrations, the S term cancels. And so at high substrate concentrations, we're limited by how much enzyme we put in there at the beginning. And so the amount of enzyme will dictate. And so these are the 2 equations that define the 2 parts. So at low substrate, it's first order in substrate. At high substrate, it's first order in enzyme. So the only way we can speed up the reaction is double the amount of enzyme. We double the amount of enzyme, then we can double the rate. But nothing's going to happen because we have too much substrate, not enough enzyme. If we don't increase the enzyme. And the same thing at low substrate, the more enzyme we have, the better. If we double the amount of enzyme, we should double the reactant. All right, so I had a question on chapter 14. What was that number? Number 14. Chapter 14 or chapter? Both. Chapter 14 and 14. Chapter 14, number 14. The following data are obtained for the initial rates of reaction A plus 2B plus C yields 2B plus E. And so this is multiple reactants. For multiple reactants, the only thing we're going to get is the rate law. So the rate is going to equal K, A to the M, B to the N, C to the O. We can't say it's first order in A, second order in B, and first order in C because we don't know. Is that a simple collision or not? It just looks like a net reaction, so we'd have to figure out. And if it were a simple collision, it would be a 4-molecule collision, which would be extremely unlikely. So this has got to have some other mechanism. This has just got to be the overall or net reaction here. But there's an easy way to figure out what M, N, and O are, and that's by doing this. And so if we look at experiments 1 and 2, 1 and 2, B and C don't change. However, A is cut in half. And so if A is cut in half and the rate gets cut in half, then we say that it's got to be first order in A. And so M has got to, little m has got to be 1, based on that. All right, then let's look at 2 and 3. Between 2 and 3, A stays the same, C stays the same. And if it's the same concentration, it's not going to have any impact on the rate. And so the only thing that's changing is B. And so we cut B in half, what happens to the rate? That's 1/4 R2. So if we cut the concentration in half and the rate gets cut by 1/4, then we say it's second order. And so N has got to be 2. And so that leaves O, only thing we have to figure out. And so let's look at experiments 3 and 4. Is that the best? No. Let's look at 1 and 4. 1 and 4, there's a problem because it's in terms of R3. So let's look at 3 and 4. That's probably going to be the easiest. So looking at 3 and 4, what's the difference between going from 3 to 4? Well, the difference between 3 and 4 is we're going to double A. If A doubles, it's first order in A, so it's just 2 to the first. And then we're going to double B. Yeah, so this would be 2 to the second power. And then we're going to do, what are we doing with C? We're going to half C. And so this is going to be 1/2 to the O power. And that's going to see what impact on the rate. The impact on the rate is it's going to be 16-fold increase in the rate from R3. And so this is going to be 16 times R3. And so what is it? Well, 2 times 2 squared would be 8. Divide both sides by 8, we get 2. 2 is equal to 1/2 to the O power. Therefore, O must equal, it's got to be -1. And so this is kind of an unusual reaction. M is 1, B is 2, and O is -1. And so what are the reaction orders with respect to A, B, and C? That's what we got. What is the value of R5 in terms of R1? So let's go to R1 and then R5. And so let's see what we're doing, going from R1 to R5. So 1 to 5 is this. We're going to 1/2 A, so that's 1/2 to the first. 1/2 B, so that's 1/2 squared. And then 1/2 C, that's 1/2 to the -1. And so if we just add up these, this is going to be 1/2 to the or we'll just multiply it out. This is going to be 1/2 times 1/4 times 2. So 1/2 times 1/4 is 1/8 times 2 is 1/4. And so the rate will be 1/4 the rate of 1. So that would be the answer. Let's see if there's another part. And that's all they want us to do. We could do more. For example, we can figure out what K is by just plugging in. Actually, we can't because we don't have any numbers. If we had some numbers here, we could figure out what K is, but we don't. All right, were there any other questions from chapter 14? Okay, do you remember chapter 7? Yeah? No? You'll want to review some of chapter 7. Probably not all of it, but some of it. So for example, do you remember which of these three you used for the definition of a system in chapter 7? Did we use open system, closed system, or isolated system in chapter 7? You remember which of these three we used? C, isolated. For a couple of problems, we used an isolated system. Just for a couple of homework problems, but for the most part, like 99% of the problems we did in chapter 7, we used. Yeah, we used B, closed system. Now, we use a closed system, but there are two types of closed systems. Do you remember what the two types of closed systems, what they are? The two types of closed systems, we use a closed system with a fixed volume and a closed system with a variable volume. This is showing a closed system with a fixed volume, right? With a closed system with a fixed volume like this is dangerous. One, because what if this reaction starts to generate gas? What do you think is going to happen to that stopper? It's going to shoot out from the top. You know, pressure is going to generate, and pretty soon that stopper. So what you can do is you can super glue that stopper on there or something, or fix it on there. But that's dangerous because what happens if enough pressure builds up that the glass could explode, right? And send glass shards everywhere. And so when we do a closed system with a fixed volume, we don't like to use glass. We like to use heavy-duty steel, like stainless steel or something, thick walls. In fact, we don't want it to explode like a bomb, so we call it a bomb, right? We call it a bomb, so it, it's not supposed to be a bomb. It's not supposed to explode. It's supposed to be able to contain that pressure, right? And so for a fixed volume closed system, we use a bomb. And a bomb is not going to explode. We wouldn't use glass like this. This is a bomb, right here. And so we don't call it fixed volume, we call it constant volume. Constant volume means it's fixed, right? We call it constant volume closed system. We don't call this variable volume here. You know what we call this? This one, if the pressure builds up, the lid can rise up, compensate for that. So we don't have any explosions occurring. But this is a closed system. Closed systems can exchange energy with the surroundings. In this case, they can also exchange work with the surroundings. But do you know what we call this one? This is variable volume closed system. We call this a constant pressure reactor. This is a constant pressure reactor. The bottom is a constant volume reactor. So we have two types of closed systems, this one and that one. Now, in a closed system, matter is not exchanged with the surroundings. The only thing that's exchanged is energy. And when we exchange energy, do you remember the first law of thermodynamics? First law of thermodynamics is that any exchange in energy between the system and surroundings will be in the form of heat and work. Do you remember the first law of thermodynamics is change in energy is equal to Q plus W, heat and work. In a constant pressure apparatus like this, both work and heat can be exchanged with the surroundings. In a constant volume apparatus like this, only heat can be exchanged. No work is going to be exchanged with the surroundings. And so this brings us to energy. We have U and H. What's the difference between U and H? Which one do we use more, U or H? We use H more than U. What's the difference between H and U? H is called the internal energy, or the total energy. I'm sorry, did I say H? U is called the internal energy, or the total energy. U is equal to the kinetic energy plus the potential energy. This is the total energy. Well, if U is the total energy, then what is H? The partial energy? 1/2 energy, 1/4 energy? What is H? So if U is the total energy, then H must be the partial energy. True or false? That's false. Both are actually the total energy. Well, how can both be the total energy? Well, this is why you want to go back and review chapter 7. You want to go back and review the relationship between H and what exactly is H and U. What it boils down to is this. When we deal with constant pressure, and do you do most of the reactions in a bomb, or do you do it out in the open lab? We do it out in the open lab, and technically we aren't really in a closed system, but in thermo, to do calculations, we want a closed system. We don't want matter leaking out. And so for calculation purposes, we'll do everything in a closed system, but we do a constant pressure closed system, not a constant volume. With constant volume versus constant pressure, the reaction is different. Here, when we do it under constant pressure, then we're going to get, delta H. If we do it under constant volume, we get delta U. As the energy change. And so that brings us to thermodynamics part 2. Thermodynamics part 2 is, we'll need some of that stuff from thermodynamics part 1. So we'll just review it as it comes along. I don't have much time to review the stuff from Chem 1A. But in thermodynamics part 2, we're looking at spontaneity, spontaneous change. Spontaneous changes have a driving force, like ice melting. Ice melting at room temperature, there's a driving force here. But this robot here, is there any no, it's not moving. This doesn't occur spontaneously. This is a non-spontaneous process, so what we have to do is we have to force this by twisting this spring, and then it would go. But this one, there's no spring to twist, there's nothing to force. It just melts naturally at room temperature without any external help. And so just briefly, this is kind of a long slide, but basically, spontaneous processes will occur without intervention. Non-spontaneous require intervention. And so that's what I call the driving force. It doesn't tell us the speed. Both these processes are spontaneous, but the kinetics of them are quite a bit different. Here, ice melting at room temperature. Here, iron rusting at room temperature. This reaction is extremely slow, but both of these have a driving force associated. And so what is that driving force? Well, people are thinking, what is the driving force? So I talk about the driving force in the reactions. The driving force for chemical reactions is going from strong oxidizer to weak oxidizer. Strong oxidizer, unstable, right? High energy, very reactive. Weak oxidizer, stable. So we're going from high energy to low energy. In other words, we're going down in energy. Strong acid, high energy. Weak acid, low energy. And so that's driving force. High energy to low energy. Ions, floating around in solution, high energy. Ions coming together to precipitate, low energy. So precipitation. And in physics, it's the same way. High gravitational potential energy. If I let go of this, it's going to drop to lower gravitational potential energy. And so this is what was thought. It was thought that spontaneous change occurs in the direction in which the enthalpy, or the energy, enthalpy would be the energy at constant pressure, of a system decreases. And you should be able to predict it. That's the way I told you to predict the chemical reactions in Chem 1A, but sometimes we're wrong. Because sometimes what happens is this, sometimes, like say for example, if I let the pen go down here, it would shoot up here, right? And so it spontaneously go from low energy to high energy. The first time you saw that was in chapter 7. Actually, I should have left that. Normally we want to go from high energy to low energy. So if the system, let's take a look at the system. If the system starts off at high energy and goes to low energy, then energy is conserved according to the first law of thermodynamics. And so what's going to happen is that energy goes somewhere. That energy goes into the surroundings. And so here we mix the solute with the solvent, and the temperature increases. And so this is exothermic. We see an increase in temperature. Room temperature is about 25. And that's what we expect. We expect it to be spontaneous because we're going from high energy to low energy. But it turns out that some solutions, when you mix the solute with the solvent, the temperature actually goes down. If the temperature goes down, that means it's taking energy from the surroundings. That means that the system is undergoing endothermic. And so this is like the pen starting down here. You mix it, and spontaneously it rises up here, sucking heat out of the surroundings. That's happening spontaneously. Would you ever see the pen spontaneously shoot up? No, not without outside intervention, right? But here, chemically, you would see this spontaneously shoot up without any outside intervention. And so what that means is there's more to it than just energy. And back in chapter 7, the more to it that they said is this. There are two factors. The first factor is in spontaneous processes, we have to look at both the energy, since most of our reactions are under constant pressure, we want the enthalpy to go down. And we want something else to go up. This something else is given the symbol S. This something else is called entropy. And so these are the two driving forces in nature. One is to minimize energy. And the other is to maximize entropy. Now, what is entropy? Entropy, S, is a measure of disorder. So things spontaneously go to a more disordered state, not the opposite. We can see that here in this slide. Here, this is an ideal gas. An ideal gas, if we look at the total energy of an ideal gas, the total energy of an ideal gas is equal to the kinetic energy plus the potential energy. I'll use this symbol, potential energy. For an ideal gas, the potential energy is 0. Because ideal gases, what are they made out of? They're made out of nothing. What kinds of chemical reactions do ideal gases undergo? None. What kind of intermolecular forces do they have? None. And so the potential energy is 0. And so ideal gas, the only energy is kinetic energy. Now kinetic energy is directly proportional to temperature. And so if we say that the initial temperature is 25 degrees C, then that's the energy of this gas. And after the expansion here, let's say we open this valve, the total energy here, well, it's 25 degrees C. It starts at 25 degrees C, it ends at 25 degrees C. There's no change in energy. However, there is a change in disorder here. And so here you can see all the molecules are in the left flask, but after we open this, then the molecules distribute themselves between both flasks. And so here, in this case, it's more ordered, more constrained. Here, it's less ordered, less constrained. There's another way of thinking about disorder, and that's positional entropy. And that is, how many different positions can we have? The fewer positions that these can occupy, the more constrained and the more ordered it is. The more positions that these can occupy, the less constrained and the less ordered it is, and the more disordered it is. And so what's driving this? Well, we know that when we open this valve, it's going to distribute itself. Energy is not driving this. What's driving this is an increase in entropy or an increase in disorder. So, all we have to do then is to figure out, this. This is for the mixing on that previous slide. All we have to do is figure this out. And so let's look at some examples. Let's say the entropy increases and the energy goes down. So this is good. This is good. And that means this should be spontaneous. So we're increasing entropy, decreasing energy. It's good, good, spontaneous. Let's go with decreasing entropy and increasing energy. Well, this is bad. This is bad. And therefore, this is non-spontaneous. The problem comes when we have a conflict. And so the conflict would result like the increase in entropy, this is good. But at the same time, we have an increase in energy. This is bad. And so it depends on which one wins. If entropy wins, then it's spontaneous. If energy wins, then it's non-spontaneous. And so we have to figure out how to weigh these. And the same thing, if entropy goes down, that's bad. But if energy goes down, that's good. And so we don't know. This might be spontaneous or it might be non-spontaneous, depending on which one of these is more dominant. So how can we tell what's going to happen? Well, we know what's going to happen with the energy because delta H calculations should be pretty straightforward. Delta H. And so in chapter 7, you learn different ways to calculate delta H. What's the easiest method of calculating delta H? Easiest probably way of calculating delta H is by doing calorimetry experiments. What do you do? No. It's probably by using Hess's law. That's the easiest. And we're using Hess's law with delta H as a formation. It's probably the easiest. But what about delta S? How do we calculate delta S? Should we take a break? Let's take a break. We'll talk about how we calculate delta S.